Hello everyone. We're going to finish up our carbohydrate section and get started into the lipids today. Last class we just introduced the biochemistry and started in on monosaccharides and disaccharides. So now we're going to look at the polysaccharides. And all polysaccharides, which you mentioned earlier, are 100% native glucose. They are an energy storage, but they are short term. And once again, as I said, shape and function are completely linked because all three of these, starch, glycogen, and cellulose, are all 100% glucose. But the way they are put together is what gives them their different properties. So starch is what you're going to see in plants. And, right, like potato, carrots, things like that. So there's many ways in which plants can have massive starch storage. Glycogen, you're going to see this in animals. So where we store ours is in the liver, and we also in the skeletal muscles as well. Those are the muscles that move you around. And then finally we have cellulose, which of course is plant cell walls. So these are not energy, these are all about structure. Okay. So if you just take a look, we'll be talking about the structures here, but you can see the structure here looks different from this, even though they're all glucose, which is a little bit of a structural difference here. Okay. Regardless, they're all polymers, right? And the monomer, again, being glucose. And they are all insoluble in water. So this is what really makes them good for storage. Not so good for transport like glucose is, but because they're insoluble in water, there is no osmotic gradient problem like there is with glucose if you wanted to store it. All right, looking a little bit more in their structures for starches. As I said, the storage, there's sort of two kinds. This part here is really for IB. So amylose and amylopectin. One is, we talked about what branches are. Those are side chains off the main chain. So amylopectin tends to be more branched. Amylose tends to be more unbranched. And this also helps with some of the properties here. You actually can buy this in the store, except it's not called amylopectin. It is just simply called pectin. And if you have ever done any canning or your family's done any canning, there are like to make jams or jellies, things like that. Depending on the type of fruit you're going to use, it can be extremely runny, like think like a syrup, or think very, very thick, like a jelly, jam sort of in between there. So what's the difference? It's the amount of thickening agent, in this case pectin, that you can use. And some fruits make very runny stuff, so you have to add lots of pectin, and others you don't need to add hardly any kind of a thing. All right, and then there's the idea there. So as why is it's good storage? Okay. And then glycogen here. So that, as I mentioned in animals, you saw it as more highly branched when you look at the image there. Therefore, it's more compact, makes it easily to fit into your liver. And as I mentioned, the muscle cells basically are skeletal muscles. Okay, now this part here is going to be strictly for IB. So both of these polymers, whether it be starch or glycogen, and either starch, amylose or amylopectin, all right, they have a particular type of bond in between their glucose units, and it is called a 1,4. Sometimes you'll see it written like this, 1,4 as well. That's possible. Okay, glycosidic. So it means it's a carbon-oxygen-carbon bond. So this is going to be one monomer. And this is the next glucose. And it's oxygen single bonded to on either side there. All right. And that is in the main or the unbranched part. All right. So the bond is formed between, remember you have to know those functional groups, the hydroxyl there, the OH group of each glucose there. Okay, and remember that the 1 and the 4, that is from counting carbons. You can go back and look at, we talked about glucose, how we start with the carbon number 1 and work our way around to carbon number 6, all right? So it's always between carbon number 1 of one monomer and carbon number 4 of the next monomer, right? Now, but to make a branch, it changes bonds. And again, this has to do with just spatial geometry of molecules, which we're not going to get into. And this is a 1,6 glycosidic bond. So it is between carbon number 1 and carbon number 6 there. So this is actually easier to think about if we look at some images that we see on the next slide here. Okay, so this happens to be a small portion of amylopectin, because it's got its branch there. All right. So this is going to be your main, this is your linear section. All right. And this is going to be your, so remember now, how would you know where carbon number 1 is? So remember I said, find this because that's going to be carbon number 6, right? And then here you're going to get carbon number 5, 4, 3, 2, 1, right? That's the way you can always kind of figure out. So there is carbon number 1, and here is going to be carbon number 4, all right? So there is that right here. That is that 1,4 glycosidic bond, all right? 1, 2, 3, 4, and then we've got 5. Okay, and then this is carbon number 6. All right, and then here is where we're going to have a branch. And again here, remember this is 6, 5, 4, 3, 2, 1. And so the bond here, right? So that's a carbon-oxygen-carbon bond. There is your 1,6 bond. And you'll notice when you get back into the branch here, within the branch here, this is going to be a 1,4. So within the branch, it's a 1,4. Between the branch and the main chain is a 1,6. All right, so that's the 1,4 versus the 1,6. So all the starch, whether it be amylose, amylopectin, or glycogen, all right, they all use this 1,4 to make the main chain, and then branches to bond a branch. It's going to be 1,6. All right, let's take a look at the next slide. So here you can see just the idea of the big molecule. There's your amylose, and here's your amylopectin here. And again, this part here would be the branch. Okay, now we have to take a look at cellulose. So cellulose is long fibers, long linear fibers, all right? And it has what we call these sort of amorphous regions, which are a little less rigid, you can see. Crystalline, think of like a crystal structure, so it's going to be more rigid. And so if we were to take a look, because each one of these, where I'm checking, is a cellulose molecule. So long chains of glucose held together, but there's interactions in between them. So what they're saying here is that it is hydrogen bonding, intermolecular forces there, that hold these molecules together here to make these nice long linear chains that are attracted to one another. All right. So cellulose is considered to be unbranched, but instead of using alpha glucose, we are now going to be using beta glucose. And I should have thought about this, but when we're looking at starch and glycogen, remember those are all alpha glucose. All right. So cellulose goes with the beta glucose. Remember, that is where the hydroxyl group on carbon number 1 is on the top part of the molecule versus rather than being the bottom half of the molecule, if you will. All right. And it is, as I mentioned, a structural feature. It is not used as energy storage. And here I mentioned the crystalline structure, gives it its strength and box-like shape, and the amorphous, which I said was a little less rigid, helps for to allow the cell to curve just a little bit, especially when its central vacuole fills with water. So between the two, crystalline and amorphous, you get strength with some flexibility, so that the cell doesn't burst, kind of a thing. Okay, and I should mention this entire slide is IB. Okay. All right. Now, it is the one polysaccharide that we don't digest because we lack the necessary enzyme to break it up. All right. As a matter of fact, I can only think of maybe one organism. It's a tiny microorganism that lives in the gut of termites. So often they say termites can digest wood. Well, actually, no, it is the protozoan inside their gut. They have a symbiotic relationship, and that protozoan has the enzyme that is able to actually break the bonds between the glucose molecules, the beta glucose molecules. Okay. Now, what we do use, so even though we can't use cellulose in our diet, this part here, I should mention, this is both IB and regular. All right, we use it as fiber. All right, and this allows in your large intestine your poop or fecal matter to pass through, so that you're not having waste, because anything that's in your large intestine is now considered to be waste. There is a little bit of nutrient extraction that can still happen due to gut bacteria, and we'll talk about that in our digestive when we get to the parts of the digestive system. But it is really important that you have regular bowel movements because this fecal matter, remember, is waste. It's toxic waste to us. And if it's allowed to sit there for too long, then you can actually it can increase the chance of the cells of the large intestine becoming damaged over time. And if you get damaged cells, then you have an increased chance of a particular type of cancer known as colon cancer. So fresh fruits and veggies are, or things that have lots of grains in them, really good for your body. Okay, now let's just take a look here. This slide here is fully IB, all right? And so this gives you a little bit of idea of the beta bonds here, all right? So beta glucose can only form a 1,4-glycosidic if one molecule faces up, so to speak, and the other one faces down. So, and this has to do with the, again, so that the two molecules can actually fit together relatively well. Because remember, these are three-dimensional molecules, not two-dimensional like we show here. So here where you have remember here's carbon number 6 here, where you have them in what we would call a cis formation. Not that you have to know that for IB anymore, but these are on the same side kind of a thing. This is not going to work. All right, these molecules will not fit together that way. But if you have carbon number 6 here and then across from it in sort of like a trans look kind of a thing, trans pattern, then this one is okay. So one facing upwards, one facing downwards. Okay. All right, so that finishes off our polysaccharide, our carbohydrate area, and we're just going to get a little bit started into the lipids. So I sometimes tend to use lipid and fat interchangeably, but the idea here is lipid is the proper biological term, which includes fats, which are typically your solids, and of course oils, which are typically your liquids. There is no general formula like we had with the glucose, where we had a 1 to 2 to 1 relationship between the atoms. There is just lots of carbon, hydrogen, and oxygen. These all tend to be very insoluble in water. If you think about vinaigrette salad dressings where you have oil and water base, you have to mix them up to get a little bit of immersion there, but leave them and you'll get the oil and the water separating after a while. All right. So lipids are considered to be nonpolar because, of course, water is a polar substance. They are long-term energy storage. So remember we said starches are short-term energy storage. These guys are long-term energy storage. They're used to insulate, so provide warmth in colder areas. They provide protection around vital organs, like your eyes. Because remember, your eyes are surrounded by a bony socket in your head, so and eyes are quite delicate, so don't want them getting scraped up. Kidney is another one. Even the heart should have a little bit of fat around it, kind of a thing. Now, unlike the carbohydrates that had 3 monomers, remember glucose, galactose, and fructose. All right, these are made up of 2 monomers. Okay. One of the monomers being glycerol. It's a 3-carbon chain, and the OL, those of you who know your organic chemistry, it's from the alcohol family. And then the other is a variety of fatty acids. And it's the fatty acids that can be different. That's what gives you your different lipids, is the type and size of the fatty acid. The glycerol is pretty much standard there. So, fatty acids, they can be considered to be a saturated fat. In other words, there is no carbon-carbon double bond, right? So all the carbons look like this, right? They have one line in between them, so on and so forth, right? Okay, so that's your saturated. versus unsaturated, where there is at least some carbon-carbon double bonds. So you'll have carbon single, then we have a carbon double. So there we go. 1, 2, 3. Put a hydrogen here, here. There we go. Okay. So that's the difference there. And then polyunsaturated, poly meaning many, so this would be many carbon-carbon double bonds. Monounsaturated means there's just one. All right. Right, so the next here shows you an image. All right, and I've circled, these fatty acids are a type of carboxylic acid. So remember, these are those functional groups. And I put them in here because this is not what determines if a fatty acid is saturated or unsaturated. This is a carbon-oxygen double bond, not a carbon-carbon double bond. You have to look at this long chain here to determine whether the fatty acid is unsaturated or saturated. So this is what we call a line diagram. And remember, wherever the 2 points meet, it's always carbons and hydrogens here. And again, I know if you haven't done any of the chemistry, this can be a bit confusing, but these are carbon-hydrogen atoms. All right? And here is how we show a double bond in one of these line diagrams. Saturated, these are all single bonds, right? So remember, we ignore the end of the molecule, the acid group. That's not what's going to tell you whether it's saturated or unsaturated. It is all the other part of the molecule. Okay. Properties of saturated versus unsaturated. You do need to know these. So we've already done the bonds. Saturated is what we could tend to talk about in fats. Animal source, they tend to have slightly more energy. They have a higher melting point, so that's why they are solid at room temperature. Unsaturated have these double bonds. They tend to be a plant source, so you see them a lot in oils. They have a much lower melting point. Thus, if you think about like canola oil or olive oil, avocado oil, they're all liquid. Whereas saturated, think about lard or butter, or think about a hunk of meat that's sitting on the counter that's got fat on it. It's solid and white. All right. Okay, so this here is all IB again. The whole slide here is all IB. Okay. So just a few more slides here. All right. So the shape around each carbon is known as a tetrahedral shape. Again, if you haven't done bond chemistry, you're just going to have to learn that. Okay. And those are in the unsaturated sections. We don't have to worry about the shape around the saturated. Okay. And so they talk about this zigzag pattern. So again, it's up, down, just like we saw right in the previous diagrams. All right. These are the same kind of, these molecules are the same. They're just showing them in slightly different manners. This one has the tetrahedral shape, and this one is just straight up a linear shape. Okay. Now, oh yes, I forgot about this. So the shape around the double bond is known as trigonal planar, all right? And because of this, this gives the fatty acids a kink in their shape, all right? So unsaturated, you can see these are long, linear. Where you have the double bonds here, right? So these are where they have the double bonds. You can see it, you get these little K shapes almost, right? These little. So this means that you have, in these long linear ones, you have lots of London dispersion. Okay, sorry, you don't need to know London dispersion. So lots of intermolecular forces. Because of these kinks, they tend to be less closely packed. So they're further apart. So you have less intermolecular forces. So forces between the molecules. And that's why these are liquids. And that's why these are solids at room temperature. It's all about the chemistry. Okay, one more slide. We can do one more slide. All right. So just like with our carbohydrates, lipids are made by dehydration synthesis, or IB speak, condensation, reactions, and broken down by hydrolysis. So here you get a chance to see there is your glycerol, right? And these are the 3 fatty acids. And there is going to be your water molecule that's going to be pulled off, right? Dehydrate to pull off water. And then you're going to make your lipid, your lipid, all right? And of course, there's going to be 3 waters because you're adding 3 fatty acid chains. So there's your 1, 2, 3 waters. Okay. And notice, now we talked about the different lipids because of the different fatty acid compositions. So notice that this one here is saturated. This one here is also saturated. But this one is unsaturated. Okay, and now because we have 3 fatty acid chains here making up this lipid, this is called a triglyceride. Okay, tri meaning 3. And then this word glyceride, remember we had disaccharide, like saccharide, or the ose ending indicating a carbohydrate. Well, glyceride means that you have a lipid. So when you gain, just when you're looking at, buying crackers or something like that, and you're looking at what they contain, if you see, monounsaturated, like that would be like this, right? Because it's only got 1 double bond there, or polyunsaturated, or completely saturated, or you see that's a diglyceride, well, then you only have 2 fatty acid chains, and this last one doesn't bond, kind of a thing. So at least now you know maybe a bit more about what you're putting into your body when you're buying stuff from the stores, and these words are not so mysterious anymore. Okay, we're going to stop right there.